High-energy physics currently faces a challenge with 10-dimensional frameworks. While these models capture complex mathematical requirements, they produce a vast range of possible realities, making it difficult to extract specific, testable predictions. In string theory and ADS/CFT, the 6 extra dimensions occupy a global background shared by every particle in the universe. This architectural choice requires these dimensions to be compactified at a scale far below our ability to observe them. Stabilizing the parameters of a universal background creates a landscape of 10 to the 500th power possible vacuum states. This immense volume of variables has historically prevented these theories from predicting the specific masses of observed particles. The geometric substrate, or GBP framework, keeps the 10-dimension count, but shifts the location of the extra 6. In this model, the dimensions wind entirely within the interior toroid of each individual particle. Localizing the dimensions inside the particle boundary removes the need for a global compactification parameter. The focus shifts from a landscape of possible universes to the unique geometric properties of a single, repeating structure. The foundation of this interior geometry lies in the Minkowski metric. This equation measures distance in spacetime and assigns a negative signature to the time dimension, setting it in direct opposition to the 3 positive spatial dimensions. Standard field theory treats this minus sign as a useful bookkeeping tool. It accepts the numerical result without necessarily defining the physical mechanism that forces time to subtract from the spacetime interval. Physicist Paul Dirac successfully navigated this metric to describe the electron. His 4-component spinner operates with high precision because it is built to inhabit the specific structure of this minus-plus relationship. In wave mechanics, a minus sign separating temporal and spatial derivatives identifies a tension substrate resisting displacement. It describes how a medium pulls back when pushed. The GBP framework interprets this as a physical axiom. Time is a one-dimensional string under tension, and the 3 spatial dimensions are transverse deflections against that tension. Physics dictates that any uniform transverse load applied to a tension string creates a parabolic curve. Following this logic, the interior geometry of a particle is defined by these parabolic boundary conditions. To remain stable, the parabolic deflection of the time string must close back on itself, mapping a continuous wave onto a discrete circular lattice. To find the correct lattice for our universe, we apply the known requirements of quantum field theory as filters. Condition 1 requires integer winding for phase stability. Condition 2, the spinner double cover, dictates that it takes 720 degrees of rotation to return to a starting state, which limits the lattice modulus, n, to even numbers. Condition 3 requires the lattice to be Mobius compatible. This allows for the broken time reversal symmetry necessary to match the spacing of energy levels observed in complex atomic nuclei. Condition 4 requires the lattice to possess a prime winding numerator, which allows the model to maintain the mathematical structure of an Euler product. Finally, to account for the 5-fold structure observed in the electroweak sector, the lattice must host a Z5 subsymmetry. 30 is the minimal integer that satisfies all 5 of these group requirements simultaneously. It is the product of the first 3 primes, 2, 3, and 5. MOT 30 emerges as the unique minimal geometry capable of hosting the symmetries required by a unified theory of the strong and electroweak forces. We can now calculate the behavior of a wave moving across this 30-step circular lattice using standard Fourier decomposition. In a circular system of this size, any wave path that shares a common divisor with 30 will encounter destructive interference. These composite modes cancel out, leaving no observable signal. The only paths that survive this interference are the 8 coprime integers, 1, 7, 11, 13, 17, 19, 23, and 29. This result is confirmed by the Euler-Totient function, which calculates exactly 8 surviving winding lanes for a 30-step lattice. These 8 lanes correspond precisely to the 8 generators of the SU3 gauge group, the mathematical heart of the strong force. In this model, the 8 gluons are the physical manifestation of the surviving interference lanes on a mod 30 topology. This geometry creates a distinction between the particle's interior and its exterior. The gluon is the path taken through the internal bulk, while the quark is the projection we observe on the exterior boundary. Translation between these two views follows Malice's law. The mass we measure is the projection of that internal winding onto our observable boundary. The parabolic geometry yields a specific projection formula. P of r equals sine squared of r pi over 15. This geometric formula is algebraically identical to the Lucier-Wise action coefficient used in lattice QCD. Physicists use this coefficient to make discrete numerical models on supercomputers accurately match the data flowing from experiments in particle accelerators. While lattice QCD adopted this coefficient to align calculations with reality, the GBP framework derives it from the geometric boundary conditions of the toroid itself. To test the model, we apply these projection weights to the surviving mod 30 lanes and compare the results to the known masses of hadrons. The weights accurately predict the observed masses across the light octet, charm, and bottom baryon sectors. Across 54 particles, the geometric projections yield a mean absolute percentage error of 0.2498%. This level of agreement is achieved without tuning variables, adjustable moduli, or free parameters. Additionally, the total topological charge of these 8 lanes equals exactly 7/2. Setting this topological charge equal to the beta function coefficient aligns the internal geometry with the observed rate of change in force strength. This mathematical balance requires exactly 6 quark flavors, matching the 3 generations of matter we observe in nature. The standard model describes the behavior of matter with incredible accuracy, relying on gauge symmetries as foundational axioms. The geometric data suggests that these symmetries, U1, SU2, and SU3, are the continuous macroscopic limits of a discrete mod 30 coprime winding. Quantum field theory serves as a highly detailed map. The evidence suggests that the local discrete topology of mod 30 is the physical terrain that the map has been describing all along.